talked about the first part of this paper, or I think it was earlier this week. I don't know. I had this really low energy stream earlier this week because I had a, had a rough morning, just work stuff. But and so I am reading this structural model approach to causal explanations. This, I don't think that when people talk about causality that this stuff gets enough play, because if you think about, well, number one, this explanation stuff is where this has to do with how humans generate explanations for things that they observe, for the evidence or the observations that they make in the world. And this has very strong implications to artificial intelligence, because if you can formalize this, if you can turn it into an algorithm, then you can get something that's very close to reasoning about the world using the same causal mechanisms and cognition that humans have. And right, so, and of course, causality and explanations are quite linked. And so last week I looked at part one, which kind of introduced this idea of actual causality. And interestingly, I didn't realize this. I'm not sure how I missed this. I'm not sure I did miss it. I think I just forgot. But there's this book by Jim Halpern here, or Joseph Halpern, sorry. That's not it. Joseph Halpern. It's called Actual... this actual causality book. And right, so let's look at this. Defining causality and such related notions as degree responsibility, degree responsibility, degrees of blame, and causal explanation. Causality plays a central role in the way that people structure the world. We constantly seek causal explanations for our observations, but what does it mean what does it even mean that an event C actually caused event E? The problem of defining causation goes beyond mere philosophical speculation. For example, in many legal arguments, it's precisely what needs to be established to determine responsibility. The philosophical literature has been struggling with the problem of defining causality. This is Hume in this book. All right, this is a lot of jibber jabber. All right, so we're talking about. All right, so this actual causality. So it goes to arrive at a definition. So this seems very kind of like philosophical, navel gazing, right? Like, what is causality? But it actually turns out to be super useful for reinforcement learning applications and also in other kinds of sequential decision-making processes, because it's about policy learning, right? Like when you're trying to, this idea of responsibility and blame, you do an action, you're an agent, you're performing actions in an environment, and those actions affect the environment, and you get some kind of results, some kind of cumulative reward that you now want to reason about. You say like, okay, well, counterfactually speaking, which is counterfactuality is a concept from causality. Counterfactually speaking, had I done another intervention, I'm the bot, had my policy produced something different to do, some other action, would I have gotten a better outcome? And so now you got to go back to those actions that you committed and try to figure out which actions actually caused this reward. And if you could figure that out, then you could figure out how to improve your policy so that you will do better in the future. And arguably, much of what reinforcement learning now does it doesn't look at actual causes, but rather looks at things that correlate with, actions that correlate with good outcomes. As we know in real life, and I think this is one of the fundamental struggles that reinforcement learning is trying to get over. As we know in real life, just because you play the game well doesn't mean you're going to win. And so, and just because you, and if you played a certain way and you lost, doesn't mean that the way you played it was responsible for your losing. And so, getting to that question of actual causality, I think, is especially when it comes to explanations, I think it's going to be, well, I think it's going to be game changing once we figure it out. Once we figure out how to algorithmize it. Well, we know how to algorithmize it. Once we get it to work on non-trivial applications like, something in AI, OpenAI Gym, I think is enough to kind of make a pretty broad impact. Anyhow, so I actually might just go with, this. If we look at the table of contents here. Yeah, see, like this idea like sufficient causality and necessary causality, this stuff comes up in when you really want to ask what the whole point of this causal stuff is when it comes to machine learning. I think like some of the more powerful applications that we haven't really seen come to fruition yet will turn up in agent models and Markov decision processes and reinforcement learning. And anyway, so let's dive into part 2 of this paper. So that book probably, so I might actually just pick up that book and just kind of read that in future versions of this stream. But because a lot of these, they're papers. Papers are always kind of like way unnecessarily hard to read, but let's see how far we can make. I gotta jump in 37 minutes for a call, but we'll see how it goes. We'll see how far we can get into this. We propose new definitions of causal explanation using structural equations to model counterfactuals. The definition is based on the notion of actual cause as defined in a companion paper. Essentially, an explanation is a fact that is not known for certain, but if found to be true, would constitute an actual cause of the fact to be explained, regardless of the initial uncertainty. Okay, so he's defined actual cause. And actually, I've already forgotten half of that paper because it was, well, I didn't forget half of it, but I forgot a lot of it because it was just pretty dense and it was very formal. And when it comes to formal stuff, I got to read it a few times. But let's see if we can't find a nice online definition. Actual causality. Is that a nice? And it's just this book again. Okay, so what does this say? Oh, well, it's about the same guy. So I guess Halpern is the person to look to when it comes to actual causality. So let's see if we can actually find a formal definition of actual cause. No, I want an informal definition of actual cause. Shoot, I guess we're stuck with the formal one. Let's see here. All right, in this section, I gave the HP definition, I guess it's him, of causality and show how it works in a number of examples. But before I give the definition, I want to define a formal language. Okay, let's just jump to the definition. The types of events that the definition allows are as actual causes are ones where we have some kind of conjunction of a bunch of Boolean outcomes. So like that certain variables take on certain values. So these conjunctions of primitive events. This is often abbreviated as, x, what do you call that? Vector, as x vector equals, you can't say x bar, you can't say x hat. I used to have a word for that. As x equals small x. I'm just going to say x equals small x. Nope, can't do that because we have these. So I'm going to say x vec equals small x vec. The events that can be caused are arbitrary Boolean combinations of primitive. So we can cause an arbitrary Boolean combination of primitive events. The definition does not allow statements of the form A or A naught is a cause of B, right? Like we see that that's typically what we see in a DAG, right? We see like a directed graph. It'll be like this node is a cause of that node, but we're not doing that here. We're saying that a node taking a value is a cause of another node taking a value. And although this could be treated as being equivalent to either A is a cause of B or A naught is a cause of B, however, statements such as A is a cause of B or B naught are allowed. What? What happened here? This definition does not allow statements of this form, although this could be treated as being equivalent to either A is a cause of B or A naught is a cause of B naught. However, statements such as A is a cause of B or B naught are allowed. This is not equivalent to either A is the cause of B or A is a cause of B. Okay, well, that is an example of why these papers suck to read. Note that this means that the relata of causality, what can be a cause and what can be, I don't know what relata means. What can be a cause or what can be caused depend on the language. How? How does all this jibber jabber mean that we got to translate it into relata? Like what can be caused and what can be a cause and what can be caused. So this is what we know can be. Okay, so this can be an actual cause. Okay. So our language, so I'm trying to understand why this is a language construct, because we're talking about logic and conjunction of events. It is also worth remarking that there is a great deal of debate in the philosophical literature about the relata of causality. And you know what, like, I'm gonna read this. There was an actual, I think, okay, there might be a video. It might be better just to watch videos. The relata of causality. So I guess he means that folks don't agree on what does it mean to say, what can, oh yeah, because like all those potential outcomes folks are like, no causation without manipulation and all that. So, I need some music. I don't know how to play music on a stream without triggering a whole bunch of DRM stuff. But let's try. I guess if it's like super old, right? Like if you play like opera music, can they ban that? Oh. Nah, they got like copyright on everything these days. Maybe I'll try this. I'm gonna try this instrumental study Spotify list. And if I get yelled at, then so be it. Can you hear that? Yeah, look at that, it's nice and relaxing. All right, so a lot of causality. So people talk about that. It's also worth remarking that there's a great deal of debate in the literature about the relata. Although it is standard in that literature to take the relata of causality to be events, exactly what counts as an event is also a matter of debate. I do not delve into these issues here. See the notes at the end of the chapter. I shall not, sir. Although I have been talking up to now about the HP definition of causality, I will consider 3 definitions, all of the same basic structure. JP and I started with a relatively simple definition that gradually became more complicated as we discovered examples that our various attempts could not handle. One of the examples was discovered after our definition was published in a conference paper, so we updated the definition for the journal version of the paper. Later work showed that the problem that caused us to change the definition was not as serious as originally thought. However, recently I've considered a definition that is much simpler than the two previous ones, which has additional merit of dealing better with a number of problems. It's not clear to me that the third definition is the last word. Moreover, showing how the earlier definitions deal with the various problems that have been posed lends further into insight into the novelties and subtleties involved with finding a definition of causality. All right, man, this guy's giving his life story. Let's get into it. X vec equals small x is an actual cause of, I always forget what that is. Is that a psi? Let's Google it. It's a phi, damn it. It's an actual cause of phi in a causal setting M and small u hat, u vec. If the following, so M is the model, so this is your assumptions of the model. This is some exogenous setting of the exogenous variables. These kind of how you think of them as the config file for your model. That's not right. No, think of it as a random seed for your model. So I also am forgetting what that mathematical notation means. So I'm going to say supports, and I don't know. Let me look at my Greek letters. Phi and what's that bit about when it's all curvy on top like that? This is what I literally did like most of my first year in statistics. My statistics PhD was like looking up, well, not most of it, but I spent a lot of time looking up Greek letters. Yeah, I guess that it must be psi. Right? What else could it be? I didn't know there was to it. It's not rho. And it's not an actual, did he write it in text? Can I Google? Nope. That'd be too easy. All right, so he's got, all right, so let's see. Whoa, I'm just sorry. I'm just looking at my Twitch here, and some craziness is happening. Must be happening on the internet. I'm gonna switch. Okay, I can't tell if it's. All right, that should be. That maybe I fixed the problem. I don't know. All right, so we got an actual cause. This model and this exogenous variable, I think this means implies or, man, never really was good at this sort of thing. So that, all right, we want to know if this is an actual cause of this. And I think this is some other Boolean set of outcomes. And we need three conditions. And the first one is that I think that the model allows these events to even happen. Right, so that's this cause, this putative, this potential actual cause taking this outcome is actually admitted by the model, and that the same thing is true of the actual effect of the effect. Number two is something else. Number three is that whatever conjunction we have in this thing here it's as small as possible, right? Like we're not adding a whole bunch of unnecessary things to it, so it's gonna be minimal. Great, and then so I think so it's so these are just kind of like, yeah, it's got to be possible, and like we can't just throw a bunch of hair onto, throw a bunch, like it has to be like beer, it can't be the froth on top. But two is saying like, all right, in the first two versions of the definition, all right, wait, where does two get explained? Is it here? All right, great. So I start by considering them AC. So he's got a whole bunch of, he's going to write his whole backstory of definitions, but fine. AC2A is a necessary condition. It says that for this x vect equals small x vect to be a cause of phi, there must be value x prime in the range of x such that if x is set to x prime, phi no longer holds. So say that again. It says that for x to be equal to x to be a cause of phi, there must be a value x prime in the range of x as, so like this x the random variable. So there must be, okay, so like in other words, there's some, so forgetting about the ranges, like, we're just assuming that we're not doing crazy stuff, but we're just saying like, all right, x is this variable, takes on these outcomes, and I could set x to some outcome where phi no longer holds. So in other words, if phi, so if x is Robert turns on the light, and so it has, if x is it has two possible items in its range, like Robert turns on the light and Robert turns off the light, and if phi is light goes on and light goes off, or light is on and light is off, then there is some value for x where, so let's say phi is light is on, and then there is some value for x where light is on is not true. And so if I change, so x prime here would be Robert makes the light, turns off the switch, and phi no longer is true there. So let me say that again. X has two outcomes. Switch is on and switch is off. Phi is the Boolean event light is on, and there is some value of x where phi it doesn't hold. So here we're saying that like phi can happen here, and x can happen in our model, and then in two we're saying like, all right, well, if there's some values of x where phi is true, and some values of x where phi is false, and that makes sense. Like there's some, if I put the light on, the value of x where phi is true is switch is on, and the value of x where phi is false, switch is off. But this is for the but-for clause. This is the but-for clause. But for the fact that x occurred, the outcome phi would not have occurred. So we saw that in the Billy Susie rock throwing example in chapter 1. The naive but-for clause will not suffice. We must be allowed to apply it again under contingencies. That is, under certain counterfactual settings where some variables are set to the values other than those they take in the actual situation, and held to certain values while other variables change. For example, in the case of Susie and Billy, we consider the contingency where Billy does not throw. Okay, so this is some kind of counterfactual example from chapter 1, whatever. Is this the entire book? Oh, crap. Huh, I think it is his entire book. So, Okay, so this is the formal way of saying that, and it has to do with partitions and disjoint subsets, and we're not gonna worry about that. So using statistician notation, if phi is y bar or y, is that I can't even tell. Let me make that bigger. Whoa, too big. Anyway, I should have done the beginning. Sorry. If blurry y equals small blurry y, then the displayed formula becomes what? What's the displayed formula? So I guess this is like y for given in okay, so this is the observed outcome, and this is, you're just saying that for some intervention, do X and do W, Y no longer takes this outcome. Okay, so this is like this is counterfactual notation. So this is just saying that this is like Hume's definition of a cause, that that doing Y leads to phi, and had Y not been done, phi would not have happened, or phi would not be true, I guess. So roughly speaking, it says that the but-for condition holds under the contingency W equals W. So this is something that's novel here, this idea of a contingency W. I think that they point out in some of their other papers that if this changes, you get problems. We can think of the variables in Z as making up the causal path from X to. All right, so this is all from the formal definition. Okay, so we're just kind of talking about but-for causation here, and then he goes through a whole kind of history about what this is all about. It's all about AC2. So I worked through some examples. I want to jump back into this paper. We're not going to get far now, but now we know what an actual cause is, and I guess we'll be looking at an explanation as a potential actual cause. So the automatic generation of adequate explanations. When did I actually finish reading this? Okay, so the automatic generation of adequate explanations is a task essential in planning, diagnosis, and natural language processing. A system doing inference must be able to explain its findings and recommendations to evoke a user's confidence. However, getting a good definition of explanation is a notorious difficult problem, which has been studied for years, and references therein for an introduction to and discussion of the following issues. So in the first part of this paper, we gave a definition of actual causality with structural equations. Here we show how ideas behind the definition can be used to give an elegant definition of causal explanation that deals with many of the problematic examples discussed in literature. The basic idea is that an explanation is a fact that is not known for certain, but if found to be true, would constitute an actual cause of the explanandum, regardless of the agent's initial uncertainty. Note that our definition involves causality and knowledge. See, I want to think about this in the context of generative models. Like I tend to think of, I come from a probabilistic programming background. Like if I generate an outcome, a sample from my model, is that sample like from a process that has, that's explicitly modeling causal relationships and dependencies in a data generating process, is that sample an explanandum? Oh, sorry, an explanation? Because that makes sense, because every sample is a possible. I'm not the only one thinking about this. My guy knows Zena at MIT has also been talking in these terms. I should sync up with him. Maybe one of these days we'll live stream a call. Note that our definition involves causality and knowledge. Following Garden-For's, we take the notion of explanation to be relative to an agent's epistemic state. What counts as an explanation for one agent may not count as an explanation for another agent. We also follow Garden-For's in allowing explanations to include fragments of a causal model. To borrow an example from Garden-For's, an agent seeking an explanation of why Mr. Johansson has been. All right, sorry, somebody sitting over there and making noise are gone now. What are we talking about? Following Garden-For's, we take the notion of explanation to be relative to an agent's epistemic state. What counts as an explanation for one agent may not count as an explanation for another agent. Okay, great. We also follow Garden-For's in allowing explanations to include fragments of a causal model. To borrow an example from Garden-For's, an agent seeking an explanation of why Mr. Johansson has taken ill with lung cancer will not consider the fact that he has worked for years in asbestos manufacturing a part of an explanation if he already knew this fact. What? So it will not consider this fact. Okay, I've seen this in the literature before for explanations, just if it's already it's stuff that's kind of already commonly known tends not to be included in explanations. It's always surprising things. That's interesting. I wonder if this applies to conspiracy theories. For such an agent, an explanation of Mr. Johansson's illness may include a causal model describing the connection between asbestos fibers and lung cancer. On the other hand, for someone who already knows the causal model but does not know that Mr. Johansson worked in asbestos manufacturing, the explanation would involve Mr. Johansson's employment and would not mention the causal model. Wait, an explanation? Didn't really follow that. So what counts as an explanation? Keep going. Where our definition differs from that of Garden-For's is in the way it is formulated in terms of the underlying notions of knowledge, causal models, actual causation, and counterfactuals. The definition is not based on probabilistic dependence, statistical relevance, or logical implication, and thus is able to deal with the directionality inherent in common explanations. While it seems reasonable to say the height of the flagpole explains the length of the shadow, it would sound awkward if one were to explain the former with a letter. All right. So we're not just this you see everywhere, and when people talk about explanations, it's not just statistics. Statistics is implied by explanation and causation, but it's not. You can't go. It's not defined by these things, right? Because you wouldn't say. You would say the height of the flagpole explains the length of the shadow, but you wouldn't say the length of the shadow explains the height of the flagpole. But those two things are symmetric in terms of correlation. So, oh man, he does a lot of just preamble, doesn't he? The best judge of the adequacy of an approach are the intuitive appeal of the definitions and how well it deals with examples. We believe that this paper shows that our approach fares well on both counts. The remainder of this paper is organized as follows. In section 2, we review the definitions of causal models based on structural equations. In section 3, we give basic definition of explanation. Probabilities added to the picture. So let's partial explanation and explanatory power. I think this might be where things get nice, because that's where we can actually connect it. There's probabilities added to the picture. That's where we're going to be able to connect it to generative models. Section 3, let's go. And sorry, dear reader, you might not know a lot of these causal modeling semantics, but this is, I'm not going to be able to kind of use what, I think this paper was written back in the day too, so whatever archaic notation they're using, I don't want to bother myself with. So, as we said in the introduction, many the definitions of causal explanations have been given in the literature. The causal approaches in the philosophy literature, such as Hempel's deductive nomological model and Salmon's statistical relevance model, because they are based on logical implication and probabilistic dependence, respectively, fail to exhibit the directionality inherent in common explanations. So those two things are too symmetric, in other words. We need something that says, from here to here. Despite all of the examples in the philosophy literature on the need for taking directionality, for taking causality and counterfactuals into account, and the extensive work on causality defined in terms of counterfactuals in the philosophy literature, philosophers have been reluctant to build a theory of explanation on top of a theory of causality. The concern has been one of circularity. In this section, we gave a definition of explanation based on the definition. Circularity is avoided, blah, blah, blah. Let's just get to the definition. Great. The definition of explanation is motivated by the following intuitions. An individual in a given epistemic state K. So this is what I know about the world, right? Ask why. Damn it. What is that thing? This is bugging me. I think it's rho. It's not rho. That's not. What? Oh, it is phi. It's just like cursive phi or something. Maybe it didn't let me copy it actually. All right, so ask why phi holds. What constitutes a good answer to this question? A good answer must A, provide information that goes beyond K, and B, such that the individual can see it, such that the individual can see that it would, if true, be, or very likely be a cause of. Where does this definition come from? So like, I ask why is water wet? And you tell me something, I don't know, that's that bad example. Like, why do we have holidays on the weekends? No, why is a knife sharp? Let's do that. I like that one, because we can have two reasons why. We could say because it's been sharpened, or because it's for cutting stuff. And so one of those is teleological, one of those is mechanistic, but like, or functional rather. So let's see how this makes me land on that example. So like, such that the individual can see that it would, if true, be, or very likely be a cause of phi. All right, so can see, what does that even mean? It's like, oh yeah, I can see that this would extend the boundaries of K, if true. We may also want to require that phi be true, or at least probable, although our basic definition does not insist on C. I think. So how do we capture an agent's epistemic state in our framework? For ease of exposition, we will consider the case where the causal model is known and only the context is uncertain. In that case, one way of describing an agent's epistemic state is simply by describing the set of contexts the agent considers possible. Given a structural model M, vector x equals small vector x is a explanation of phi relative to some set k of contexts if the following conditions hold. That's all right. So this is like, so for each context, so we're using this mu as like explicitly defined in terms of values that an exogenous variable takes. So we haven't talked about this in this stream, what small u means, but it means it's like the random seed of this model. It's like the kind of initial conditions of this model. So for any initial condition, the model would emit this event that needs the explanandum. That we have a sufficient cause. Okay, now I've forgotten the difference between, I'm forgetting what the difference between sufficient cause and actual cause. We have a probability of sufficiency. And probability of sufficiency means that assuming that that x didn't happen and y didn't happen. So assuming that x is false and y is false, what's the probability that y would be true if x were true or made true? So there's that turning it. So okay, so it's and doing that. This event's being true is enough for this to be true. For any case where for any initial condition where this is true. Got the minimality thing, and then there's some set of conditions where this is not true, where this actual cause, so it's not like this cause is just always true all the time. Like if I said if I wanted to explain why a house burned down, I wouldn't say because oxygen is present, because oxygen is always present, no matter what the initial condition is, right? So this just says that the agent considers a context possible where the explanation is false, so that the explanation is not known to start with, and considers a context possible where the explanation is true, so that it's not vacuous. I think that's what I just said. I'm going to come back to this hopefully next week, Tuesday. Soon we'll get to some code. Like there's this OpenAI paper. The Ortega is the guy's name, maybe. Causal. Pedro. Anyway, there's this algorithms for causal reasoning and probability trees, and there's a Jupyter notebook out there somewhere. And this actual causality thing will fit in quite nicely with how they've set up here, because probability trees do a much better job at representing events like this, as opposed to like this actual causality is all in terms of events, right? Well, this stuff looks a lot more like events than what you normally get in a DAG. And probability trees are great for things like I work on at Gamelon, namely natural language processing. Gotta go, I got a meeting, but thanks for signing in or tuning in or whatever. Talk to you next week.